Hi, I'm Julia Watson, and I'm going to be talking about generalization of creative constructions in the wild. Creativity is an important aspect of language that enables us to communicate new ideas and nuances of meaning. For example, if someone has seen verb plus up constructions like she was wrapped up in a blanket, they might creatively generalize to say something like, he slept burritoed up last night, meaning he was wrapped up like a burrito. However, creative language use is constrained. For example, the creative generalization, she bookshelved up the novel, sounds kind of awkward, and this points to something bigger. People seem to have strong intuitions about which creative usages are acceptable, even when they've never heard them before. And how creative language use is constrained is a key question for cognitive science of language. There's lots of work on this topic, and here I want to mention 3 papers of particular relevance to this work to highlight the kinds of methods that have been used. Suttle and Goldberg used an artificial language learning experiment to examine how people extend novel argument structure constructions. This Bybee and Eddington paper used a survey approach where they asked participants about acceptability of certain verb usages. More recent work has looked at modeling generalization in a historical context. Like this 2016 Perec paper looked at use of a creative verb construction over time, but they used koha, a relatively formal corpus. And the key question that we take a first step towards addressing in this work is, how do people use creative constructions in the wild? And we do this by looking at creative verb usages from social media data. So on the previous slide, I described the approaches researchers have taken to understand generalization, but I didn't talk much about what specific factors have been discussed. In approaching this topic, there are 2 key groups of factors that affect generalizability. The first kind is inherent generalizability factors, which are properties of a construction that make it more or less generalizable. One factor from this group that we're particularly interested in this work is variability, which has to do with how spread out the types of a construction are in semantic space. For example, the set of types shown here are all semantically related and have to do with putting on clothing. And if these were the only types for this construction, then we would say it has low variability, and low variability constructions are thought to be less generalizable. The next set of factors has to do with how well a possible usage of a construction fits with that construction, and the most obvious example is semantic similarity between the potential coinage and the set of existing exemplars. Here, flannel up fits well with the set of exemplars we see for this construction, since it also has to do with putting on clothing. And we use the term fit function to describe how good of a fit a potential coinage is for a construction. And the 2 questions we address in this work have to do with better understanding fit functions. And in particular, one question we want to investigate is how variability influences assessment of fit. And another question we're interested in is which exemplars matter most in assessing fit, high or low frequency exemplars. In order to address the first question, which asks whether the importance of similarity differs depending on a construction's variability, we need a pair of constructions that differ in their level of variability. And for that, we look at 2 denominal verb constructions. Denominal verbs are nouns used as verbs, and there's a lot of really interesting work on them. A key idea that's relevant here is that denominal verbs are formed by taking a participant in an event and making that the verb. So an example from our corpus is fingernailed the edge of an ace for later, which means to mark the edge of an ace using a fingernail, where fingernail is the instrument participating in the event, and we see it being used as a verb. The examples we've looked at here so far are bare denominal verbs, and we contrast these with our second denominal verb construction, which is denominal verb particle constructions, or denominal VPCs. So an example here is hydro up, meaning to drink water, where hydro is the verb and up is the particle. And specific particles select for different kinds of verbal elements. For example, there are several constraints on what kinds of verbs can occur with the particle up. One such example is that up is most compatible with verbs where there is a sense of positivity. So friend him up sounds better than enemy him up. And because of these kinds of constraints, we expect VPCs with a given particle to have lower variability than the broad set of nouns that can occur in bare denominal verbs. To keep things simple, we focus on VPCs with the particle up, but we've also tested this on the particle out and found similar results. For each of the constructions we consider, we want to build two sets of types. A set of types that reflects the diversity of examples speakers are exposed to, which we refer to as exemplars, and a set of novel usages that we expect most speakers haven't seen before, which we refer to as coinages. And we can use the set of exemplars to predict what we find in the set of novel coinages. We built these sets by collecting data from Reddit, which is a great source for naturalistic creative language use. To build the coinage sets, we took a sample of one-off types, and this is based on the idea that our corpus is large enough that one-off types are novel to most people. To build the exemplar sets, we included types of varying frequencies, which is intended to capture the distribution of types that a person might have seen. We didn't just take the high-frequency types because we're interested in testing the idea that low-frequency examples play an important role in generalization. This shows sample exemplars and coinages for each construction we look at. We use word-to-vec embeddings as our semantic representations. For denominal verbs, we take the embedding of the verb, and for denominal VPCs, we take the embedding of the verbal element of the VPC. And this shows the number of types available in word-to-vec for each of the constructions we look at. I mentioned before that we expect denominal verbs to be more variable than denominal verb particle constructions. Before we move on to looking at our two questions of interest, we want to make sure that the variability of the two constructions is actually different. And the approach that we take to measuring variability is to cluster the exemplar embeddings using k-means, and then compute the similarity between each exemplar's embedding and its cluster centroid. So here you see an example of a clustering with two clusters, and the purple squares are the cluster centroids. And the measure we use takes the sum of cosine similarity between each exemplar embedding and its cluster centroid. And we do this for 1 to 20 clusters. And these are the results that we find. Note that because this measure is based on similarity, higher scores mean more semantic similarity among exemplars and therefore less variability. And this confirms our prediction that denominal verbs have higher variability than VPCs with up. So this means that we can use these two constructions to test ideas about how generalization plays out for constructions with different levels of variability. And this brings us to our first question of interest, which is, does the variability of a construction affect the importance of similarity in assessing fit? Previous work by Suttle and Goldberg tested this idea by running an artificial language learning experiment which drew on knowledge of English semantic verb classes. Applying this idea to our two constructions of interest, if the instances of a construction you had seen were semantically similar, like in a low variability construction, then you would probably extend it to other similar usages. For example, flannel up here is similar to this cluster of denominal VPCs. But for the high variability construction, where the existing types have less in common, we might expect to find novel coinages like fingernail, which are less clearly related to the set of exemplars we've seen before. Suttle and Goldberg showed this was the case in an artificial language learning experiment focused on comprehension, and here we build on this, looking at production and exploring how constructions are used in the real world. And we test this idea in two ways. The first is an extremely simple approach. For each creative coinage, we take the cosine similarity between that coinage and its nearest exemplar, and we call this maxsim. And we expect to find that denominal VPC coinages fall nearer to their existing exemplars and have a higher maxim, since they are less variable. And this is exactly what we find. This result suggests that variability modulates the importance of similarity in generalization, in line with the results of the artificial language learning experiment from Suttle and Goldberg. Although this first approach is simple and intuitive, it abstracts away from the mechanisms of category extension assumed to play a role in the process of generalization. We address this issue in our second approach, which models the growth of each construction using models of semantic category extension, including prototype, exemplar, and nearest neighbor chaining models. We train these category extension models on the exemplars and use that to estimate how likely the novel coinages are as extensions of that category. And we compare how likely true coinages are, like flannel up in this example, to the likelihood of a set of unattested examples, like tower up, dog up, and apple up here, which are essentially a collection of random nouns from our corpus. And we compare them by creating a ranking of attested and unattested examples and looking at where the attested coinages fall in this list. If the true extensions of a construction have relatively low ranks, like flannel up here with a score of 1, this would suggest that the category is fairly restrictive and only allows coinages that are a good fit. And we expect that denominal VPCs, the less variable construction, will be more restrictive and have lower coin fit scores. And we find that this is the case across all of the category extension models we tried. The lower bars for denominal VPCs indicate that true coinages are ranked lower and are more similar to existing exemplars. So summing up for Q1, both approaches agree that similarity matters more in the extension of denominal VPCs, which are the lower variability construction. Another question we're interested in this work is which exemplars matter most in fit functions, and especially whether high or low frequency exemplars matter more. So in this example, is the low frequency exemplar sweater up more important in generating novel coinages like flannel up? Or is the high frequency exemplar gear up more important? Based on the existing literature, there's reason to expect either might be true. On the one hand, work by Bybee and Eddington showed that similarity to high frequency exemplars is predictive of acceptability. And based on this, we might expect people to produce examples that are more similar to high-frequency exemplars. On the other hand, work on morphological productivity has argued that a high proportion of low-frequency examples can signal that a construction is productive. So for example, seeing a lot of cases like Lady Gaga-esque might make people realize that they can apply the suffix esque to many different nouns. We're interested in exploring the idea that low-frequency examples might also signal where in semantic space a construction is productive. To test this idea empirically, we first take each creative coinage and find the frequency of its nearest neighbor exemplar. So for flannel up, we would look at the frequency of sweater up. And we did this for nearest neighbor exemplars for all coinages and took the mean. And we compare this to the frequency distribution for all exemplars for the construction. Our hypothesis is that creative coinages are more likely to emerge near other low-frequency items, so we expect that the mean frequency of nearest neighbor exemplars will be lower than the frequency of the average exemplar. And we find this to be the case for both constructions. In these plots, the density curves are the bootstrapped mean frequencies based on all the exemplars, and the solid green lines are the mean frequency of the nearest neighbor exemplars. And for both constructions, this is significantly lower than the mean exemplar frequency, which may suggest that novel creative extensions of constructions emerge near low-frequency examples. We think this is a really interesting initial result, and we're excited to build on it to further investigate the complex relationship between exemplar frequency and generalization. For this work, we wanted to better understand how people extend creative constructions in the wild. And to do this, we performed the first large-scale analysis of creative generalization of verb constructions leveraging social media data. Our first question was, does the variability of a construction affect the importance of similarity in assessing fit? And we found evidence for this in line with earlier work. This was the first demonstration of this effect on production in the wild. Our second question asked whether high or low frequency exemplars matter more in fit functions, and we found that novel creative coinages emerge near other low frequency expressions in semantic space. This hypothesis was inspired by research on morphological productivity, and it's a novel finding in the area of semantic generalization of language. Thank you.